very much. So we saw now in the previous talk a very nice introduction into the topic. So radiation cancer therapy is used to kill cancer cells, and it is actually, in the meantime, quite well known that it is not only the primary radiation that damages the DNA, but it is mainly the secondary particles that have very low energy. And as Ilko was pointing out, this is the basic mechanism that outlines the DNA damage. So water is ionized, producing secondary electrons, ions, and radicals, and they can attack the DNA to lead to the actual DNA damage. And the electrons are particularly interesting because they form these transient anions that effectively dissociate, and this can then lead to a strand breakage here. And to study the underlying molecular mechanisms of this electron attachment, very often model compounds are used to understand these processes. And the most simple model compounds are nucleobases, DNA nucleobases. And these are very often studied, and in the meantime, the interaction of electrons with nucleobases are quite well understood. But the properties and the interactions, they might change already when we just combine two of these nucleobases, and then we have additional interactions like nucleobase stacking and hydrogen bonding between the base pairs. And so the properties of single and double-stranded DNA might be quite different from the behavior of the single nucleobases. And as was also pointed out in the previous talk, DNA is actually located here in an aqueous environment. So we are interested in studying more complex systems, but well-defined systems, and determine absolute strand break cross-sections in these complex environments. So this is the outline of my talk. So I will present three different topics. First of all, we developed a strategy how to determine strand break cross-sections, and we use this and irradiated oligonucleotides with low energy electrons. And we are interested in the question of how the sequence of the oligonucleotides modifies the strand breakage, and if there is an effect of the secondary structure of DNA. And we applied the same technique to study also photon interaction with DNA, and we used photons around the ionization threshold of DNA. And in the last part of my talk, I want to present an experimental approach where we try to study electron-induced processes directly in solution. So, first of all, to determine strand break cross-sections, we didn't use the traditional biochemical methods because this is not suitable for various reasons when we go to oligonucleotides. So we use oligonucleotide targets that we attach to platforms. So we have here a triangular platform, and the oligonucleotide targets that we want to study are attached in a certain pattern. And we image these structures. First we deposit them on the surface, and then we image this by atomic force microscopy. This has several advantages because then we can identify this pattern, we can identify the intact strands after irradiation, and in this way we can directly compare multiple sequences within the same irradiation experiment. And basically, this is done on a single molecule level, and from this we can, in a very straightforward way, determine absolute cross-sections for strand breakage. And what you can see here, this platform, this triangular platform, is also made from DNA. And we use a technique from DNA nanotechnology, which is called DNA origami. So we actually, this is the whole platform with the target strand is one DNA molecule, and this is formed by self-assembly. And the principle is shown here. So we use a long single-stranded DNA with more than 7,000 nucleotides. The sequence of this strand is well known, and then short artificial nucleotides oligonucleotides are added, and they are complementary to one part of this scaffold strand, and the other part is complementary to a remote part in this circular strand. And when it comes to hybridization, this is stapled together, and therefore we call these oligonucleotides, these shorter ones, staple strands. And we add a larger number of these staple strands, and depending on the sequence that is chosen here, we can then form or fold this scaffold strand into more or less any arbitrary two-dimensional shape, for example, into this triangular shape here. And here in the zoomed in, you can see these crossover structures of this scaffold strand. And this is a typical AFM image of triangular structures, so they simply form by self-assembly. So this all looks quite fancy, but it is very simple to produce. So we simply add them together and heat it up and let it cool down, and then we end up with these triangles. And then we can modify each of these staple strands individually. And we modify them by extending them with our target structure that we want to study. So we can distribute these target structures on different positions on the triangle and identify these positions by atomic force microscopy. And the overall strategy is shown here. So we use these platforms with the target strands and irradiate it, for example, with electrons, and this leads to strand breakages here in the target strands. And by taking an AFM image of these structures, this is shown here, the resolution is typically not good enough so that we can identify directly these target strands. So we have to label the target strands with biotin, and then we, after irradiation, we simply add the protein streptavidin. This binds strongly to the remaining strands, and this streptavidin is big enough that you can identify it here as a bright spot in the AFM image. And as you can see, we can clearly identify the position, so we can distinguish different positions and in this way distinguish different sequences. And this is an example for a proof of principle experiment. So we used, we placed two different sequences on one of these triangular platforms, the blue sequences and the red sequences. This is a typical AFM image before irradiation of a control sample, and another AFM image of a sample that was irradiated with electrons of 18 eV. For these experiments, we used a very simple commercial electron flood gun from a TOFSIMS machine. So this was just to do these proof of principle experiments, and we were very limited with the electron energy here. And when you take a closer look, you can see that the number of these intact oligonucleotide targets, this decreases when we irradiate it. And then we determine the relative number of these strand breaks as a function of the electron fluence, and then the number of strand breaks increases, and in the low fluence regime we can then determine the slope from the linear fit and determine the cross-section for strand breakage. And as you can see here, the two different sequences, they behave very differently. So we have different cross-sections, and these differences can be attributed to just this, the difference in the sequence. And this was only a disulfide bond that we introduced for a test experiment to see how we can sensitize the DNA, because it is well known that disulfide bond breaks easily when it reacts with electrons. So in the next step we analyzed real oligonucleotides. So we compared different sequences that contain, apart from thymine, also guanine, adenine, and cytosine, and we determined in this way that I showed before the cross-sections for strand breakage. And we see that we could find that the adenine-containing sequence has a strand break cross-section that is about threefold higher than the guanine-containing sequence. So this was a bit surprising. So adenine oligos seem to be quite sensitive. This is surprising because the ionization cross-section is actually the highest for guanine and is lower for adenine. So there must be some additional effects that cannot only be attributed to the properties of the single nucleobases. In an additional experiment, we replaced the central thymine by bromouracil. Bromouracil is a well-known radiosensitizer, and we determined also the cross-sections here. The cross-sections are slightly larger at this electron energy, and so we can see that the bromouracil increases the strand rate cross-section, but the effect of the base sequence is much stronger. So the question is the ionization the initial step? And as I said, there must be some additional effects that account for this different behavior here of the different sequences. One way to explain this could be that it was shown a few years ago that adenine and guanine oligonucleotides can have very different electronic properties. It is well known that stacks of guanine have higher stacking interactions than the corresponding adenine nucleotides, oligonucleotides, but when it comes to the ionized systems, then it was also shown that the reorganization energy is smaller for the adenine oligonucleotide. So there is a geometry change in the guanine stacks, and this leads to the notion that the ionized states are delocalized in adenine stacks over several nucleobases, whereas guanine typically acts as a hold trap in charge transfer in DNA. So the question is, this charge here for inducing strand breakage has to be transferred to the DNA backbone. So, and we have to find out whether these different electronic properties have an effect also on the barrier for the strand break process. And this is what we want to study now in more detail. And as I said, we used so far just in proof of principle experiments a very simple machine, and now we assembled a new low energy electron irradiator at the University of Potsdam. And here we also use a quite simple electron gun, but we can control now the electron energy in a better way, and we can determine the beam profile and also the electron fluence very accurately, which is necessary for an accurate determination of absolute cross-sections. And so we are now studying different, a large number of different oligonucleotide sequences, and one interesting structure is the telomeric DNA. Telomeric DNA can be found at the end of chromosomes, and the length of telomeric DNA determines the lifespan of a cell. So the shorter the telomeric DNA, the shorter is the lifetime of a cell. And telomeric DNA consists of repeat units that are guanine rich. This is shown here, GGG, ATT. And we would like to compare and study the telomeric DNA in its linear form, but telomeric DNA is also very interesting because in the presence of cations, especially potassium ions, it folds into these quite complex structures which are called guanine quadruplex structures. And in these structures, the guanines form quartets, guanine quartets, and 3 quartets are stacked on top of each other and stabilize this quadruplex. So we can now want to compare the primary structure with a secondary structure. And we wanted to see if we can prepare these different structures selectively on the DNA origami platforms. And for this, we attached this telomeric DNA to the DNA origami structure, and we studied the folding process by fluorescence resonance energy transfer. For this, we attached 2 different dyes to the system. We excite the first dye, and when the 2 dyes are in close proximity, like in this folded state, then the excitation energy is transferred to the acceptor, and we can observe the fluorescence of the acceptor. And this is an example of a fluorescent spectrum. When we subsequently add potassium chloride, then the fluorescent emission of the donor dye decreases and the emission of the acceptor increases, indicating the folding process of this guanine quadruplex. So we can prepare these different structures and we irradiated it to determine the strength rate cross sections. And here is an example of two times repeat unit of the telomeric sequence. We compared it with the sequence where we replaced the adenine by guanine, because it was shown in a previous study that they have very different electronic properties and ionization potentials. As you can see here in this fluence dependence of the number of strand breaks, there's not much of a difference between these two sequences. And these are the strand break cross sections of different systems that we studied. So first of all, we have here the cross sections of the 2 times repeat units, and then we have we doubled the length of the telomeric DNA, and then the strand break cross section increases. And then we add potassium ions so that these telomeric DNA folds into quadruplexes, and then the strand break cross section decreases again. So it appears that, so this is here the structure, and it appears that the guanine quadruplex stabilizes the whole system, but the extent of stabilization is actually much less than we expect for double-stranded DNA. So we now applied the same strategy to study the interaction with photons. So photons in the vacuum UV region around the ionization potential. So we used actually the same technique as before. We just used photon radiation, and we used here the photon irradiation from the synchrotron Soleil in France in collaboration with Alexander Milosavljevic and Alexandre Giuliani. We used the disco beamline of Soleil and replaced these structures on calcium fluoride windows and irradiated these with photons of defined energy and dosage. And here you can see the absolute cross sections for strand breakage. These are shown here for 2 different sequences. So sequences with adenine and cytosine. And we used energies from 6.5 to approximately 9.0 eV. And we see here clear energy dependence. And this region here below the 8.4 eV is the sub-ionization region. Here the strand breakage is very small, but still it is not zero. So also at these energies we can induce strand breaks with photons. But then above the ionization threshold, the strand break cross-section increases, and then we also see a slight effect of the sequence here. So also the A-containing sequence is broken more easily compared to the cytosine strand. And in the top row here you see the absolute cross-section for photon absorption for exactly the same oligonucleotides at the same photon energies. And from these numbers we can then compare or determine the quantum yield for strand breakage. And you can see here the clear energy dependence of this quantum yield with a minimum around 7.2 eV, which is very interesting, but the quantum yield is actually the same for all the sequences, so within the error bars there's no difference, and but only here at higher energies we see a difference in the strand break cross-sections. And in the last part of the talk I want to present you preliminary results from experiments where we want to study electron-induced processes directly in aqueous solution. And for this we use gold nanoparticles. Gold nanoparticles are already discussed as potential radiosensitizers in cancer therapy, because when irradiated with higher energy radiation, then they release secondary electrons. And this also happens when the surface plasmon resonance of these gold nanoparticles is directly excited by pulsed lasers, and also electrons are released from these gold nanoparticles. And this process also takes place in solution. So we did a very simple experiment. So we used a solution that contains gold nanoparticles and nucleobases. And we irradiated this with the pulsed green lasers that excites the surface plasmon resonance of the gold nanoparticles. And then electrons are released, and these can then attach to the nucleobases, induce, depending on the structure of the nucleobase, dissociation reactions. And then when we have now nanoparticles in solution, we can use surface-enhanced Raman scattering to detect the products that are formed during the irradiation. So surface-enhanced Raman scattering is a very sensitive technique to determine the chemical compounds present in the solution. And these are spectra that we obtained, Raman spectra. So these are vibrational spectra of thymine in solution after different times of irradiation with the pulsed green laser. And the spectra, they look quite complicated, and I just want to turn your attention to this region here at higher wave numbers, because there are several bands appearing in this region, and so these are completely new bands. And for example, the band at about 2,100 wave numbers can be assigned to the stretch vibration of the C and triple bond in Cn minus. And these bands in these regions, they increase with almost linearly with the irradiation time. And so we can assign these bands with the decomposition of the ring structure of the aromatic nucleobases. And we also looked at bromouracil as a comparison. As a very important feature, we can see that here these bands that we saw in the case of thymine, they simply do not appear with bromouracil. So apparently there is no real ring decomposition induced by the released electrons. But on the other hand, we see changes that are indicated here by the arrows. So here are two bands that disappear after a long time of irradiation. And these bands, they are associated with the carbon-bromine bond. So this means that upon reaction with the low-energy electrons, the carbon-bromine bond is broken and Br- is formed. And so this is not surprising, because this is well known from gas-phase dissociative electron attachment that was studied in quite a detail. But also these studies, it was found that the formation of these bromine ions is very effective in the case of bromouracil, but the decomposition of the actual molecular structure here is much less than compared to the non-brominated thymine or uracil. So when we form this U-H radical in solution now, so in gas phase this remains just a radical, but in solution this can just wrap hydrogen and form stable uracil. So the question is, do we have in solution a transformation from bromouracil to uracil? For this we compared our spectra now. So the lowest spectrum is just the bromouracil without irradiation. The red spectrum is the irradiation product, and the blue spectrum is the spectrum of uracil plus added bromide ions. And as you can see, these two spectra here, they are almost identical. There are some very small signals that are additionally there in the irradiation products due to additional products that can be formed. So with this I want to conclude. So we developed an effective method to determine absolute cross-sections for DNA strand breakage. We applied this to electrons, and we find that adenine might be a weak link in oligonucleotides. We compared secondary structures with primary structures in the form of guanine quadruplexes. There's a bit more research going on in this direction to understand these processes more detailed. And then we want to study these processes at different electron energies, so this has to be done. And then we studied also the interaction with photons around the ionization threshold of nucleobases. And here we want to continue the study of different sequences And we performed a proof of principle experiment in aqueous solution using gold nanoparticles as a source for for low energy electrons, and detection by surface enhanced Raman spectroscopy of the formed products. And with this, I want to thank my group, who actually did a lot of the work that I presented today. So especially I want to mention Jenny Radwitz, who assembled the new electron irradiator and did the telomere experiments. Stefanie Vogel did the experiments at the synchrotron with the BMB photons, and Robin Schürmann did the experiments with surface enhanced Raman spectroscopy. And here are the names and funding agencies, and I thank you for your attention.